Our universe is a vast and magnificent place. It's filled with wonders that stretch beyond our wildest imagination. From the smallest particles that flicker in and out of existence, to the grand tapestry of galaxies spinning across billions of light years, we are surrounded by cosmic beauty. For centuries, humanity has gazed up at the night sky, driven by an insatiable curiosity to understand our place within this grand cosmic drama. We've built incredible instruments and developed profound theories, all in an effort to piece together the story of everything. Yet for all our progress, the universe continues to hold its deepest secrets close, revealing just enough to keep us asking more questions. One of the most profound mysteries we've ever encountered concerns the very fabric of space and time itself. It's a puzzle that challenges our most fundamental understanding of physics. We once thought we had a rather good handle on the universe's ultimate fate. We believed that the gravitational pull of all the matter within it, the stars, the galaxies, and the mysterious dark matter, would eventually slow down its expansion. Maybe it would even cause the universe to collapse back in on itself in a big crunch. But the cosmos, it seems, had a different plan, a surprising twist in its tale that has sent scientists back to the drawing board. What we discovered was something utterly unexpected, something that really defies our everyday intuition about how things should work. Instead of slowing down, the expansion of the universe is accelerating. Imagine throwing a ball into the air, and instead of it slowing down and falling back to Earth, it suddenly shoots upwards with increasing speed. This is exactly what our universe appears to be doing on the grandest of scales. This astonishing revelation has forced us to confront a new and enigmatic component of our universe, a force or energy that seems to be pushing everything apart. This mysterious influence has been given a suitably enigmatic name: dark energy. It's called dark not because it's sinister, but because we simply do not know what it is. It seems to make up nearly 70% of the total energy density of the universe. The leading hypothesis is that dark energy is a property of space itself, an intrinsic energy of the vacuum. This idea is known as the cosmological constant, a concept first proposed by Albert Einstein, albeit for a very different reason. If dark energy is indeed the cosmological constant, it means that every cubic centimeter of empty space possesses a small but non-zero amount of energy. As the universe expands, more space is created, and therefore more of this vacuum energy comes into existence. However, there's a significant problem with this idea. When our best theories of particle physics are used to calculate how much this vacuum energy should be, the answer is colossally wrong. The theoretical value is about 120 orders of magnitude larger than what we observe through cosmology. This is perhaps the worst theoretical prediction in the history of physics, a discrepancy so vast it suggests we are missing something fundamental. This leads us to consider other possibilities. Maybe dark energy is not constant at all. It might be a new type of energy field that changes over time and space, something which has been given the name quintessence. These possibilities open up a fascinating new question. If dark energy is not a uniform property of space, could it have a direction? Could it be stronger in one part of the sky than another? Is this phantom push pointing somewhere? One of the most powerful tools in our arsenal is a specific type of stellar explosion known as a Type Ia supernova. These events are astonishingly bright, briefly outshining entire galaxies, which allows us to see them from billions of light years away. What makes these supernovae so special is that they act as standard candles. By carefully measuring their apparent brightness as seen from Earth, we can work out their distance with remarkable accuracy, creating a map of the universe's expansion history. But distance is only half the story. We also need to know how fast these galaxies are moving away from us. For this, we use a phenomenon called redshift. As the universe expands, it stretches the waves of light traveling through it. Light from distant, receding galaxies is stretched to longer, redder wavelengths. The greater the redshift, the faster the galaxy is moving away from us. By combining these measurements, we can build a precise record of how the universe's expansion rate has changed over billions of years. Another crucial line of evidence for dark energy comes from the most ancient light in the universe, the cosmic microwave background, or CMB. This is the faint afterglow of the Big Bang, a thermal radiation that fills all of space. Emitted when the universe was just 380,000 years old, The CMB is a snapshot of the infant cosmos. The tiny temperature fluctuations correspond to slight differences in density in the early universe, the primordial seeds from which all galaxies would eventually grow. At the very heart of our standard model of the universe lies a profound and simplifying assumption, the cosmological principle. This principle states that, when viewed on a large enough scale, the universe is both homogeneous and isotropic. However, science progresses by challenging its most fundamental assumptions. What if the cosmological principle is not strictly true? What if there are subtle deviations from perfect isotropy? Intriguingly, several tantalizing anomalies have emerged from our observations. Perhaps the most famous is a feature seen in the cosmic microwave background. The larger scale temperature fluctuations seem to be aligned in a particular direction, a so-called axis of evil. Other potential hints have emerged from different types of surveys. Some studies have suggested a dark flow, a bulk movement of galaxy clusters all streaming in a uniform direction at incredibly high speeds, difficult to explain with our current understanding. Testing this hypothesis requires incredibly precise observations. We need to look for subtle differences in the expansion rate across different patches of the sky. The predicted differences are tiny, pushing our observational capabilities to their very edge. It is a search for a faint whisper against the roar of cosmic expansion, a delicate signal that could tell us we are on the verge of uncovering new physics beyond Einstein's general relativity. The search for this cosmic signpost is on. To move from tantalizing hints to definitive answers, we need more data, much more data, and with far greater precision than ever before. One of the most powerful tools in this quest is the European Space Agency's Euclid mission, which launched successfully in 2023. Euclid will spend 6 years surveying a third of the entire sky, observing billions of galaxies stretching back over 10 billion years of cosmic history. By measuring their shapes and positions with exquisite accuracy, it will create a colossal three-dimensional map of the cosmos. On the ground, the Vera C. Rubin Observatory in Chile is poised to begin its legacy survey of space and time. This behemoth will scan the entire southern sky every few nights for a decade, cataloging billions of stars and galaxies. This immense dynamic dataset will provide an unparalleled movie of the cosmos, allowing us to track the expansion history with incredible precision across different directions, and look for even the slightest variations that could point to an anisotropic dark energy. These experiments represent a multi-pronged attack on the mystery of dark energy. By using different techniques and observing different aspects of the universe, they provide crucial cross-checks against each other, helping to eliminate systematic errors. If a directional signal for dark energy truly exists, it should show up consistently across all these different data sets. If these next-generation surveys find nothing, it will provide the strongest evidence yet that dark energy is indeed Einstein's cosmological constant. Imagine that after all this searching, the evidence becomes undeniable. The Euclid satellite, the Rubin Observatory, and other future surveys all confirm the same astonishing fact. The universe's expansion is not the same in all directions. The implications would be nothing short of revolutionary. This single finding would force us to tear up our most fundamental cosmic map and begin drawing a new one from scratch. This would be a seismic shift comparable to the Copernican revolution. If dark energy does have a direction, it almost certainly cannot be Einstein's cosmological constant. It would be smoking gun evidence for a new dynamic entity in the cosmos, a new type of energy field, or perhaps even a fifth fundamental force of nature. Perhaps this new field is a low-energy manifestation of a deeper theory, like string theory or M theory. The specific directionality would provide the first concrete experimental data to guide these highly mathematical theories. The discovery would also challenge our philosophical perspective. Our home would no longer be a random address in a uniform cosmic city, but a specific location within a universe that has a global and perhaps meaningful structure. Finding a direction for dark energy would not just solve one mystery, it would unlock a door to a previously hidden part of our universe, revealing new forces and new components of reality that we never knew existed. In the end, the quest to understand dark energy and its potential directionality is about more than just filling in a gap in our cosmological models. It speaks to the very heart of the scientific enterprise and the nature of human curiosity. It is about our innate desire to understand our place in the universe, to ask the biggest questions we can formulate. This is the engine of discovery, a cycle that continually expands our intellectual horizons. The path to answering this profound question is fraught with immense challenges. The potential signals are extraordinarily faint, buried deep within statistical noise. It requires patience, ingenuity, and unwavering commitment to following the data. The hunt for the direction of dark energy is a marathon, not a sprint. It demands not just bigger telescopes, but also a more sophisticated understanding of all the subtle effects that could mimic the signal we seek. Whether we find that dark energy has a direction or not, the journey itself will be of immense value. We continue to look up at the sky, not just with wonder but with purpose. We build our instruments, we analyze our data, and we continue to ask, is the phantom push of dark energy pointing somewhere? Does the universe have a hidden axis, a secret direction written into its fabric? At present, the universe is not telling, but humanity is listening, more intently than ever before. And the enduring power of a good question is that sooner or later, the universe has no choice but to answer. The search goes on.